Well, you guys ready? I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask you to guide our work today. Help us to just understand this technique of partial fractions and help us to glorify you in whatever we do, Lord. In your name I pray, Lord Jesus. Amen. So let's see here. So let's see, what was Dr. Sprano up to this morning? Did you guys see? Behind me? Looks like a what? I think it's a trig substitution, right? What's he got? Integral of... Integral of 2 minus x squared to the 3/2 divided by x cubed. So he made a x equals square root of 2 sine substitution for that, to do that integral, right? So we could do that, right? What would that result in? So he says, let x equal, let me rewrite this integral so you guys can see it better. Integral of 2 minus x squared to the 3/2 power divided by x cubed dx. So this will probably be our final example of trig substitution here. For a while anyway, because right after this I'm going to start what's called partial fractions. All right, so let's see, how are we going to do this one? So we let x equal to square root of 2 sine theta. If we do that, then 2 minus x squared is what? 2 minus the square root of 2 sine theta squared, which is 2 times 1 minus sine squared theta, which is 2 cosine squared theta. So what we're looking at is the integral of 2 cosine squared theta to the 3/2 power divided by x cubed, which is the square root of 2 sine theta to the cube, the third power there. And what's my dx? Well, dx is square root of 2 cosine theta d theta. All right. So we've got square root of 2 cosine theta d theta. Right? Hopefully nothing here too mysterious. Hey, I said go away. Now go away. Oh. You have to press the green button and then the red button. They're really trying to make sure that you're not. I think this is the work over here, but we'll do it ourselves. How about that? So then what's the next order of business, right? Well, algebra. We need to simplify those powers and see what we're up against. Right? Ooh, integral of cosecant cubed. Ugh. What do you think? How do you think the integral of cosecant cubed went? I think it was the end of class, so I didn't finish, but it's going to be the same as secant cubed, right? It's going to loop. You have to loop. It's like going to loop back to the integral of cosecant. So like integral of cosecant cubed, I expect is equally nasty to the integral of secant cubed, and probably in kind of the same way. All right, so I mean, I think cosecant cubed would kind of be like the cousin of that guy you meet on the elevator, right? Kind of the same, but a little bit different. Maybe he wears overalls, whereas the other guy just wears like cut-off jeans. I don't know. Let's see here. I haven't seen cut-off jeans in a while. All right, let's see here. What's going to go on here? What do we do? So you've got, what happens to the cosine squared to the 3/2? What is that? What does that mean? Cosine squared to the 3/2 is what? That cosine cubed, right? Because that's cosine theta squared to the 3/2 power, right? And the laws of exponents, multiply the exponents, so that gives you cosine theta cubed, which of course we just write as cosine cubed. So we have, what we're up against here is 2 to the 3/2 power divided by the square root of 2 to the 3rd power, right? And then you got yourself a cosine cubed theta, you got yourself a cosine theta, and downstairs we got sine cubed. And of course I also have a square root of 2 right here, which I'll just stick out here since I forgot to put it somewhere. Put it out in the front. Now, the good news is that this factor in the front is just what? Is, you know, contrast to white on white. I mean, this is just 1. That's 2 to the 3/2 over 2 to the 3/2, yeah? And so what we're up against then is the square root of 2 times the integral, apparently, of cosine to the 4th of theta d theta over sine cubed. How would we do this integral? I'm going to do it over here. Integral of cosine to the 4th of theta over sine cubed theta d theta. How are we going to handle this thing here? Oh, rats. Is that why there was a cosecant cubed over there? Oh, please let it not be so. Yeah, I think this is the integral of, maybe this is, yeah, maybe cosecant cotangent's the way to go here, actually. Maybe. I'm not sure. Let's see here. So you've got, you know, cosine cubed theta. Now I'm starting to regret taking the bait here. So this, because this was not my not my design for today. I think I may have just gotten suckered into something here. Golly, well that I can. Oof. Yeah. Nope. All right, I got to think about this for a second. All right. There may be other ways, but here's what's popping out in my mind at the moment. Now this I may have to bail on this in a second here. So I multiply the top and the bottom by sine theta. So what I'm thinking of is making a, oh golly, I'm not sure that really helped. So if I let you, goodness gracious, I don't want to do that. Well, here, let me show you where that takes us. So that takes me to u equal to, I'm going to let u equal to cosine theta. Then du is minus sine theta d theta, right? And in view of that, this is the integral. Okay, this motivates my lecture, but in a kind of weird way. So we've got u to the fourth, right? And then a minus du. And then what is sine to the fourth? Well, sine to the fourth, right, is 1 minus cosine squared theta squared, yeah? So this is really 1 minus u squared squared, right? And so lo and behold, we've got the integral of minus u to the fourth du over 1 minus u squared squared. Huh. Well, this is kind of interesting. I really shouldn't take the bait here. So I think what I'm going to do is I'm going to give myself homework in the interest of not wasting your time. And I'm going to work this out, and then I'll come back to you tomorrow with the solution going on from here, okay? So you can leave yourself some space here. We'll come back to this. Yep.
In your original integral there, can you rewrite cosine to the fourth as 1 minus sine squared and then factor it out and have 3 integrals?
Yeah, I think that would be another good way to do it. That probably would take me away from this path. And that's a good idea. So you're like, instead of doing what I did, expand the numerator, right, rather than the denominator. Yeah. And I think that's a good course of action. I think that'll actually lead to, well, now I see why we had the integral of cosecant cubed. Yeah, so that's going to be 1 minus 2 sine squared theta plus sine to the fourth theta, but that's all divided by sine cubed, right? So lo and behold, we've got, cosecant cubed theta d theta minus twice the integral of cosecant theta d theta, and then, oh, well, that's nice, plus the integral of sine theta d theta. One of these I can do in the amount of time I have to work on this today. So as you can see, the other path is also less scary in the terms of what we currently know, right? You have the technology already to solve this problem. If we took 30 minutes, right? We could calculate the integral of cosecant cubed, the integral of cosecant, we could work it out. But man, wouldn't it be nice if when we came up against something like this, we had a technique to integrate this? And that's the issue, that's the topic for today. How do you integrate rational functions, all right? So let's talk about it. How do you integrate rational functions? This is called the technique, well, this is called partial fractions decomposition. Do you guys, so how many people covered partial fractions decomposition in like your college algebra class? Okay, that's what I thought. One, you did?
Is that the AB thing where you
The A,
split it apart?
yeah, AB thing, you split it apart, yeah. But did you do that in college algebra?
Well, I took a high school algebra, but I feel like I remember the title.
You did it in high school? That's good. I think, so like the older professors here, they talk about that was like a standard topic in college algebra like 30 years ago, but it is definitely not anymore. And it wasn't a topic in college algebra when I took college algebra, and that was a long time ago. And so what is partial fractions? Well, let me just kind of give you the bird's eye view of it, okay? Just in words. Let's call it partial fractions. Partial fractions decomposition. And since I don't want to keep writing that, let's agree that that's the PFD. All right. So here's the deal. Any rational function. What's a rational function? that means f of x is equal to p of x over q of x, right? Where p of x and q of x are polynomials. That's a rational function. Like a fraction, but with polynomials. Yeah? Any rational function can be written as polynomial plus a sum of basic rational functions. The polynomial we find by long division if we need to. All right. And the basic rational functions, we determine those by that AB thing he was alluding to. All right. And just as a summary comment here, so we use like A, B, C, dot, 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 to find, for coefficients of this sum. All right, and how many coefficients do you need? Where the number of coefficients equals the degree of q of x. So if your denominator is a quadratic, you need an a and a b. If your denominator is a cubic, you're going to face a, b, c. If your denominator is a quartic, a, b, c, d. If your denominator is a quintic, a, b, c, d, e. And we can go on, right? So let's look at some examples. So that previous thing, I'm not even calling it an example. We didn't finish it. That's just a stub or whatever. I don't know. Well, like I said, I do my homework. I'll bring you back the solution. OK, so here we go. What if we had 3x plus 2 over, let's say x squared minus 3x plus 2? All right, so the partial fractions decomposition. So the partial fractions decomposition, it always proceeds from completely factoring the denominator. It's all about the denominator. So this is x minus 1 times x minus 2, right? So the partial fractions decomposition here is a over x minus 1 plus b over x minus 2. Now we're not done. So sometimes there's two different kinds of questions I like to ask, all right? So I want to make sure we understand each other about these two different kinds of questions. The one kind of question is set up the partial fractions decomposition, but do not determine ABC, blah, 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 all right? When I say that, you're done. That's it. That's the partial fractions decomposition for this rational function, right? But when I say actually find the partial fractions decomposition, determine the coefficients, we're not done, right? We need to figure out what the A and B are. How do we do that? Well,
you're going to take the numerator and multiply it by the denominator of B for A and the denominator of A for B.
Right, so you're saying multiply by the x minus 1 times x minus 2, both sides, right? Mm-hmm. So when we do that, what happens? It's just what you said, right? We get cancellation, like a strategic cancellation of, how's it go? We get 3x plus 2 is equal to a times x minus 2 plus b times x minus 1. Why is that? Do you guys see that? Do I need to write it out? I'd rather not write it out if I can. So all I'm doing is I'm multiplying this equation right here by the denominator. So on the left-hand side, the denominator just straight up cancels, right? On the right-hand side, this denominator times a over x minus 1, the x minus 1's cancel and leave you x minus 2. Over here, the x minus 2's cancel and leaves you x minus 1, right? Now this is an identity. It has to hold for all x, all right? You might be like, well, what about x equals 1 and x equals 2? Those are problematic, right? The original equation is not even defined for those. But through a quirk of the limiting process, it actually still makes sense for those numbers. There's a homework exercise at the end of Stewart about that. But anyway, you can justify that. So what we can do, the easiest thing to do with this kind of problem is just to evaluate the equation at x equals 1 and x equals 2, which is, you know, kind of ironical. The two places which seem most dangerous to look at the equation, right? They're the ones that are, that's where we should go. So x equals to 1, x equals to 2, what do you get? If I put in x equals to 1, I get what? 3 plus 2, 5 equals to what? A times 1 minus 2, which is what? Minus a, or a times minus 1. What's b? What happens with b? We'll plug in 1 there. Gone, right? b times 0. That's a nice equation. Well, how about x equals to 2? Well, x equals to 2, I plug in 3 times 2 is 6, 6 plus 2 is 8. And how about the other side? So I get a times what? I mean, I can write it out here. B times 0, right? This one is a times 0 plus b times, well, 2 minus 1, which is 1, right? So those are mighty nice equations because they tell you that a is equal to what? Negative 5. And b is equal to 8. And that we can then plug back up into the a and b, and we've found the partial fractions decomposition of this rational function. And why does that matter? Well, check it out. If we're integrating 3x plus 2 over x squared minus 3x plus 2 dx, well, that's actually the same as the integral of what? Of 8, well, fine, minus 5 over x minus 1, right? Plus 8 over x plus 2. That's what the algebra we did up there earns us. And can you integrate those? Yeah, we can integrate those all day long, right? Not a problem. These are both logs, so we got like minus 5 natural log absolute value of x minus 1 plus 8 times the natural log of the absolute value of x plus 2, all plus a constant. Oh yeah, how did my plus 2 become a minus 2? 10 decipoints off, yes. I mean, I guess I can blame women. Follow man. Eve. So it's like, am I still allowed to make that joke? I don't know. There we go. Fortunately, my channel's not monetized, so. Although I'm thinking about it. Because I think people still have to watch commercials on my channel anyway, right? No? As I heard they were like putting commercials on non-monetized channels too. Is that wrong? Not all?
In some cases.
Only the popular ones, right? Yeah, so like, my theory is that my path to like more subscribers is to come up with a good set of math pranks. If I could somehow come up with like really interesting math pranks and like do these to people unaware.
The air horn.
Ooh, the air horn. Yes. That reminds me, I was supposed to buy that last night. Oh well. He said, give the entire class an A. Haha, math prank. No. But for realsies. All right. I don't give people grades. You guys earn your grades. So anyway, let's see here. So next example 2. What if we're up against f of x equal to, oh, I don't know, x to the 4th divided by x times x squared plus 4x plus, oh, I don't know, 7. This one's a little bit tougher, all right? Suppose we want to integrate this. How do we integrate such a thing? We can use the partial fractions decomposition, all right? So first of all, the thing to notice here is that this is not a proper rational function. What do I mean proper rational function? What's that? There's an x in, oh, yeah, let me fix that. There, okay. Otherwise, you guys are exactly right. What I was about to do would have been total nonsense, because I really should have just factored the x out and made the problem easier. Thank you. I fixed that. There we go. Okay, now what? Well, the thing is, let's see here. So what I'm up against here is a quartic divided by a cubic, right? So we can use long division to rewrite this as a polynomial plus something. All right, let's do that. So I'm going to multiply out the denominator for the sake of the long division. And that's just x cubed plus 4x squared plus 7x, right? And the long division I need to do is I'm dividing x to the 4th plus 2 by x cubed plus 4x squared plus 7x. And since you guys have spent so much time in college algebra or high school algebra and synthetic division and almost no time on polynomial division, you're ill-equipped to deal with this problem, right? But we'll learn it here. If you haven't learned it already, it's not complicated, really. So to do this long division, I have to figure out what do I need to multiply this polynomial, right, in order to get rid of this x to the 4th. So I need, yeah, x times, so I multiply by x. Now x I have to multiply by this, and then I put it down here. So I go x to the 4th plus 4x cubed plus 7x squared, right? Then I subtract, and that gives me a minus 4x cubed minus 7x squared plus 2. So what comes next? X what? Minus, plus, what? What's next? Just minus 4. But right idea. Because minus 4 times x cubed gives me what? So this minus 4 times this, I get minus 4x cubed. 4 times 4, minus 16x squared minus 28x. All right? I write some parentheses here because you need to remember we're subtracting. You have to distribute the minus to the whole thing, right? Just like I did up here if you think about it. And what happens? We get the 4x cubes cancel. Minus 7 minus a minus 16 is 9x squared. And then what do we got? Plus 28x plus 2. All right. So what we now have is that f of x equals to x minus 4, right? Plus what? Plus 9x squared plus 28x plus 2 divided by, I'm going to unmultiply the denominator now, x times x squared plus 4x plus 7.
So you did the long division because the degree was higher.
Right. I did the long division because it's an improper fraction, which is to say that the original numerator has equal or higher degree than the denominator. Right? And once you do that, well, the x minus 4, we can integrate that. That's harmless, right? No problem. We got that. And then what's left over, right, is a proper rational function in the sense that the numerator has a smaller degree than the denominator. All right? Now, we need to do partial fractions on that. How does that go? What's that look like? I'm going to do it over, ooh, rats. Otherwise, I'm going to forget. Okay. giving it a second. In the past, I foolishly got right to the board and took a deep breath after doing that. It's not good. All right, so you guys are going to have to remind me. We had, what was the piece that was not the polynomial, but the other part? No, the other piece. The numerator of the, after the long division.
9x squared plus 28x plus 2.
By the way, that's called the remainder of the long division. That what I just wrote down. You notice the reason I knew I was done. You know you're done with the long division once the remainder, the last remainder, has smaller degree than what you're dividing by, right? I'm dividing by degree 3. My remainder is degree 2. I'm done. Okay, so then I've got what was it, x squared? But let me, if you don't mind, I'm going to go ahead and complete the square on that piece. So that was actually what, x plus 2 quantity squared plus what?
Plus 3.
Plus 3? Man, I need to get glasses. I'll do it over here too for you guys. X squared plus 4x plus 7 is x plus 2 quantity squared minus 4 plus 7. So yeah, plus 3, we have a winner. Very good. So that's what we're up against here. So you notice that this quadratic factor is really different than the one I faced in example 1. Yeah? Because it doesn't factor. Right? It's an irreducible or a prime quadratic. So the way we treat that is a little bit different. What we're going to do is we're going to do a over x. A over x takes care of this guy. All right? And then what we're going to do is plus b times x plus 2 plus c divided by x plus 2 squared plus 3. Now, the x plus 2 is optional. Like what I'm trying to say is not everybody agrees. So some people would put bx plus c over, x squared plus 4x plus whatever it was. 7, thank you. Some people would do that for this piece, and I mean, more power to them, but if you follow my lead, then the integration that you face after you do this is much easier. All right, as we're going to see. The integration of something of this form is really pretty straightforward. We'll get to that, okay? So how do we find the a, b, and c now? Yep.
Wouldn't a be times x plus 2 squared plus 3?
Ah. So you're saying,
It would be 9x squared plus 28x.
so you're, this,
A times x plus 2 squared.
I mean, if this was a creative writing course, I would be very disappointed in you because you just told me to do the same exact thing that we did in the last example, right? Which was to multiply by the denominator. It's the same literary device. I mean, come on. Like, some variety in the calculate. But yeah, that's what we do. 28x plus 2 is a times x plus 2 squared plus 3, which of course you could also write as x squared plus 4x plus 7, but it will serve us to write it this way. And then plus b times x plus 2 plus c all times what? All times x, right. So what's going on here is the x canceled on the a term, right? And then the fancy schmancy denominator canceled on the bx, the bc term, yep.
So why exactly did you put b x plus 2 plus c?
That is the partial fractions decomposition.
Well, I know. Oh, so where did the x plus 2 come? Why'd
because that's the partial fractions decomposition. That's how these break up.
I see what you
If I wanted to break it up in the way I broke it up in example 1, it would require me using complex numbers. So the difference is, that this is an irreducible quadratic, so to rewrite that as a sum of a number over a linear plus another number over linear would require me to introduce complex numbers for the decomposition. It's not something I've derived for you. It's just I'm telling you that's how it works. So I'm not really answering your question.
I guess I'm just confused why you put the plus C. Like, why is that part of it? Because in the problem 4 it said A and B. So what's the difference that makes you have to use
This is 1, 2, 3, third order. We expect 3 coefficients, A, B, C. The difference is with the other one, it was just a quadratic denominator, so we have A and B.
So what if that is raised higher? So that's why you divided.
Oh yeah, like the one I just erased here, we had a quartic denominator. It's going to need A, B, C, D, the one that I had with you.
Okay.
Yeah.
Is there?
Listen, I'm going to work out the details for this, and then what I'm going to do is I'm going to go down a laundry list of examples and how you'd set it up, but I'm not going to do the algebra. The algebra takes us a while, so I can do a couple of these in depth. But then I'm just going to show you how we would get started on a bunch of other problems next, okay? And I think that'll answer your questions a little bit. That's fine. There are different approaches here. There's an easy thing, which is what? You could distribute, yeah. I'm going to resist that temptation. I'm resisting that. This is an identity, right? This has to hold for all x, which means that we can plug in values of x to get specific equations of A, B, C. 0 would be a very lazy and smart move. So, I mean, it's late. So I know I'm telling you lazy is smart. Engineers will usually agree with me about that. 2, actually people in general seem to think that whatever lazy is smartest, right? You know, that guy, he didn't work for 30 years to amass $500,000. He got a scratch-off ticket and won $500,000. That's wow, that's really good. You know, I think we should have more respect for the guy who worked for 30 years to earn it. You know, he lived his life well. The other guy just, you know, whatever. So, I'm sorry. Do you have relatives who are like lottery winners? Okay, no. All right, that's fine. Okay, so the point is if I put 0 in, it kills this term, yeah?
But wouldn't you still have plus C or C times X? It's plus C. Plus C times 0.
But 0 multiplies the whole kit and caboodle over here.
I was plugging in only.
Yeah, so it's just the A term, which gives me, what, 7A? So therefore, hey, we got it. A equals 2? Apparently 2/7. That's nice. Yes? And then what? And then there are different ways you can go here. There's an easy thing to do. You see what's kind of easy here is to plug in what? Plug in A. Well, yeah, I mean, sure, but I'm just going to leave it. I think -2 stands out as a nice number for this equation because -2 makes this go away, and -2 makes the B go away, right? So -2 is a nice number to plug in. Right. I mean, it's not perfect, but if I plug in -2 to the left-hand side, what happens?
-36.
Well, yeah, I get 9. I'll write it out. 9 times -3 squared plus 28 times -3 plus 2 is equal to what? 3A plus C, you know, this just drops down to what? C times -2, right?
Are we doing -2 or -3?
We're doing -2? Oh, man. Oh, again, women. I mean, Eve. It's all her fault. Or Adam, if you listen to some preachers. Let's see here. 2 times minus 2 plus 2, I don't know. Let's see here. Okay, now, yes, I should plug in minus 2. Like, you have to, this is an important thing. You have to plug the same number into both sides. Otherwise, it does not work. That is true. Thank you. I'm going to hear about this later. So that's 36 minus 56, which is negative 20 plus 2. So what we're up against here is minus 18 equals to 3 times a. Well, that's ugly. 6/7 minus 2c, right? So we can solve for c. What's c equal to? C is equal to, 1/2 of 6/7 plus 18. Where did my calculator gone to? I know what I'm going to do. When I get home, I'm going to be like, no game time until we find Dad and his calculator. That'll fix it. 59/7. Is that right? That seems small. Because like 18 times 7 is like 70 plus 56, which is 126. 126 plus 6 is 132. 132 divided by 132 is 65. 132 divided by 2 is 66 over 7? So anyway, don't do that in your head.
One of these times.
I mean, the only people you're going to impress with that is like a generation of mathematicians that's already dead. So, rest in peace. May they rest in peace. All right, so, I mean, I do enjoy arithmetic, it's true. I don't deny it. And then what? We still need to figure out b. Just plug what? Plug everything in. There are various approaches. You can plug a number into the equation, any number you haven't done already. Yep. I'm seeing a vote for the number 1. Do you guys like that? Yes. Let's do number 1. So, I hate writing so low. I'm going to, it is what it is. I should have chose a smaller font. So 9 plus 28 is 37 plus 2 is 39. So I'm plugging x equals 1 in. So I get 39 on the left-hand side. On the right-hand side, 1 gives me what? It's often convenient to go back to what we started with. Like, this formula is easier for 1. 1 plus 4 plus 7 is 12, right? So we've got 12 equals to 12a. And then what? Yeah, plus, what do you say, 3b plus c? So we're trying to find b. This gives us b is equal to 1/3 of 39 minus 12a minus c, which is 1/3 of 39 minus 24 over 7 minus 66 over 7. Oh, you guys are going to make me calculate it, aren't you? 210 plus 63 is 273. 253, 252. 252. Thank you. All right. So what? So what? So now we can come over here, right? And we can say the integral of f of x dx, right? Well, I'm going to get, let me do it in the middle. We're done with this, right? So I can work in the middle. All right, so here we go. The integral of f of x dx, as I called it, is actually equal to the integral of what? Well, we've got the polynomial piece that we found back in, 20 minutes ago, x minus 4. Wasn't that was the most enjoyable part of all this. I mean, what am I talking about? This is all enjoyable. All right, so then plus 2/7 times 1 over x, yeah? Plus what? Where do we go? Plus 61 over 7 times x plus 2. C was plus 66 over 7 divided by x plus 2 quantity squared plus 3 dx. What's that? Oh, you got it? Okay. So a bunch of these things I can just straight integrate, right? Like the x minus 4, what's that? That's what? 1/2 x squared minus 4x. And this piece right here, well, that's 2/7 what? Plus 2/7 natural log of the absolute value of x, yeah? That's the integral of 1 over x. Then I'm going to write out a step here. Then I'm going to have plus the integral of, let me pull that 61 over 7 out. 61 over 7 times the integral of, well, what I'm really looking at there is 1/2 dw over w plus 66 over 7 times the integral of dx over x plus 2 squared plus 3. So here I made w equal to the denominator. So dw is 2 times x plus 2 dx, right? So dw over 2 was x plus 2 dx. So that we can integrate, and we've got 1/2 x squared minus 4x plus my 2/7 log of the absolute value of x plus 61 over 14 natural log of the absolute value of w, which is x plus 2 squared. It's the quadratic. It's the x squared plus 4x plus 7, yeah? And then we've got one last curmudgeon to deal with here. How do you wrangle that? I suggest we use a trig substitution. If we don't know how, we can derive that with a trig substitution, right? We just let what? I can let x plus 2 equal to the square root of 3, what? What's the identity? Tangent squared plus 1 is secant squared, right? So I want to square root of 3 tangent theta there.
Why couldn't we just do u substitution?
What u would you like? But then, if I make x plus 2, then that will give me u squared plus 3 downstairs, which is still, it's better, but. So now, so this gives me dx is root 3 secant squared theta d theta. And if you'll forgive me for not writing out every last step here, this is the integral of root 3. That's usually the sign I'm about to make an error, so watch me. And this should become 3 secant squared theta with that substitution. So that just collapses down to a d theta, right? So this whole thing integrates to theta. So then finally, answer 1/2 x squared minus 4x plus 2/7 natural log absolute value of x plus 61 over 14 natural log the absolute value of x squared plus 4x plus 7 plus 66 over 7 inverse tangent of x plus 2 over the square root of 3, and lest I lose my 10 decipoints, plus a constant. There you go. So, yep.
What'd you do with the plus 3?
Plus 3.
Plus C.
Oh, plus C? I added it to the end. Plus, which 3 are we talking about?
The dx over x squared, x plus 2 squared.
Oh, yeah, it's the one step I didn't write down. So like x plus 2 squared, it's the trig substitution. X plus 2, it's the, you know, the nice part here. So that's the square root of 3, tangent theta quantity squared plus 3. So we can factor that 3 out, and that gives us, and actually, no, your question is good. You're not wrong. I'm missing something. You know, you're right. There's an error. Where did that 3 go? That's a good question. So yeah, that was the 3 secant squared. I was right about that, but then, like I warned you, I was going to make a mistake, and sure enough, I did. See, because I basically, to write this, I've canceled square root of 3 with 3, which of course is nonsense, right? Root 3 over 3 is what? This reduces to 1 over the square root of 3, so I should have 7 root 3 here. Sorry about that. Thank you. Very helpful. So in the online classes, we're told we have to make videos for classes that aren't more than 10 to 20 minutes. This is why Calculus 2 can't be an online class. Because to properly demonstrate a technique like partial fractions decomposition, you might need 30 minutes for one problem. If you're going to do it like methodically and having a conversation about it, yeah. There are just problems like that. But once you understand the method, it'll go faster a little bit, but not much faster. But I would say this, like, it is kind of like, you think about it, somebody asks you, can you find a function that when you differentiate it, you get x to the 4th plus 2 divided by x times the quantity x squared plus 4x plus 7? And then you say, well, sure, it's just 1/2 x squared minus 4x plus 2/7 the natural log of the absolute value of x plus 61 over 14 the natural log of x squared plus 4x plus 7, take the absolute value of all that. 66 over 7 root 3 times the inverse tangent of x plus 2 over the quantity root 3. Oh, don't forget to add a constant. Said no one, right? I mean, this is really, really neat. This method that we have allows us to answer really complicated questions through a series of small but logical steps. Yep.
It's not a very dumb question, but why did you choose the square root of 3 in front of him when you did trig substitution?
It's because I want the denominator to become a single thing, right? And I know that tangent squared plus 1 is the right identity. Mm-hmm. And I know that that 3 has to somehow match up with the tangent squared term. So if I'm going to have to, I have to put root 3 there because I know I have to square the x plus 2 to get back to the 3. That's basically it.
Okay.
So
Oh, okay, I see.
I mean, it is a creative step nonetheless.
Because I was thinking just like the x plus 2 squared, but okay, I see.
Yeah. Okay, so I said we were going to look at setups, right, of different things. So let's just go down a laundry list of examples. And I'm going to set aside, let us agree that in the big scheme of things, we got to remember long division comes first for some examples, right? Don't forget about that. We don't ever have to do the polynomial piece as part of the partial fractions decomposition. I think of this as a separate thing than finding the partial fractions decomposition. When I'm talking about the PFD, I'm just talking about the sum of basic rational functions, all right? And the thing that makes the basic rational functions so awesome is that they are functions that we can integrate. Every basic rational function that I'm about to start rattling off here, we can integrate them. What does that mean? Like, well, there's a theorem of algebra that says any rational function it can be written as a sum of basic rational functions. So you put these two things together, what that means is we can write down in closed form an integral, an antiderivative for any rational function, which is pretty nice. So let's see here, setups. If, let's see here, what example am I on? Example 3. Golly. Example 3. So 13x to the 4th minus 2 over x plus 1 squared times x minus 2. All right? If this was what you're up against, oh, I'm sorry. Let me make that better. Let me make this a third power. So x plus 1 quantity squared, x minus 2 cubed. The partial fractions decomposition works out to the following. A over x plus 1 plus b over x plus 1 squared plus c over x minus 2 plus d over x minus 2 squared plus e over x minus 2 cubed.
Are we going to use the whole opposite one of these things?
Oh, sure. Example 4.
Yeah.
If we had 6x minus 7 divided by, oh, I don't know, x minus 42 to the 26th power, then that would be a over 40 over x minus 42 plus b over x minus 42 squared plus c over x minus 42 cubed plus plus z over x minus 42 to the 26th power. Indeedly. You guys want to know what those numbers are? See, when I was your age, I was blessed. I had a TI 86. Do you know what a TI 86 is? It's a calculator, that's right. But you know what it was? It was one of the first graphing calculators to have symbolic manipulation. In other words, you could take a derivative and you could calculate an integral. Now, by the time I was taking quantum mechanics, I knew how to, I knew how to find the integral of like sine cubed and integrate from 0 to pi. That's something I could do, right? That's something I can do in 5 minutes. That's something my TI-86 can do in 10 seconds. and the instructor didn't care too. It was great. So, and then it stopped working at some point. But man, you guys have so much more because you got Wolfram Alpha. And if you want to check your work on any of this stuff, man, you can check anything, right? What would I say, 26? Let's see if we can crash Wolfram. Well, that's kind of disappointing. I mean, there it is. So apparently y is equal to 6 and z is 245. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, all 0. Ooh, we're using x for a coefficient. That's kind of bad form.